Today I'll be discussing our low-powered wearable substance monitoring device. This device was created by a group of students at North Carolina State University, originally as a class project, but developed further for the purposes of this conference. Our motivation for this project was to design and develop a portable device that could monitor in real time the drug use activity of the subjects and establish recorded data that will aid in detecting or providing evidence of drug use to prospective employers. The device could also be integrated into sobriety programs to help recovering drug addicts prove sobriety to their loved ones. The device also has possibility of generating revenue through sale of the device and the associated consulting services that come with it. As the market currently stands, there is no recorded, real-time, reliable way to track drug use. The existing models are relatively easy to outsmart. The available alcohol monitoring devices are not discrete to use. This makes it difficult to integrate them into corporate environment and to use for sobriety-related programs. The market for drug rehabilitation programs and recovery systems is wide open, especially for wearables. There are several drug tests available on the market. Urine, blood, hair, saliva, and sweat are all examples of this. However, all of these drug tests are highly invasive. Here are several products that are currently available on the market but have very limited application. The solution we developed is a real-time monitoring device that gathers its input from the basic body physiological parameters. The subject's pulse rate, skin temperature, and galvanic skin conductance are the inputs to this device. Our solution is based on previous research, which shows variations in these parameters based on alcohol and illicit drug intake. Our device is easy to use, less expensive, and has a foolproof design. Our solution can also be integrated into any support platform, and concerned relatives can use it for informative monitoring. According to a report from the American Heart Association, the pulse rate of a healthy adult ranges between 60 and 100 beats per minute. Rigorous activities like exercise can shift this parameter from its baseline, but it takes a shorter time to return to its nominal value immediately after the exercise. Based on the previous research on the relationship between the pulse rate and the ingestion of illicit drugs, the pulse rate of the subject increases sharply to over 120 beats per minute once these drugs are consumed, and it takes a longer time to get this value back to its nominal state. An individual's normal skin temperature is around 33 degrees Celsius, but this value can range from 28.2 to 37.2 degrees Celsius depending on the ambient temperature. Alcohol and illicit drug consumption shows a different result for skin temperature when compared to exercise. There is an observed rise in skin temperature as a result of a drastic fall in the core body temperature because of the increased flow of blood to the skin. Galvanic skin response reflects the activity of sweat glands and the autonomous nervous system as a whole. During exercise, GSR is very low compared to when there is no rigorous activity. GSR increases sharply when there is an intake of alcohol or ingestion of an illicit drug. This increase is associated with the fact that alcohol and illicit drugs increases anticipation and autonomic arousal of the subject. This creates a physiological change and has an effect on the shift in the baseline of the GSR value. Our system can be broken down into three components: the device's hardware and firmware, our mobile application, and our device's mechanical design. Our design consisted of several components: an Arduino microcontroller capable of using Bluetooth Low Energy to transmit data, an IR temperature sensor, the TMP006, a light sensor, the SI1146, a GSR biopotential amplifier circuit. Our design also took advantage of a FRAM IC a USB controller, a LiPo charger, and a buck boost. Our design went through 2 iterations, had no major design problems, and was fabricated through Oshpark services. The boards had a minimal cost of $85 to produce, were 4-layer and 2-sided. Here you can see the top and bottom sides of our printed circuit board. The bottom side was assembled using a reflow oven, and the top side was assembled by hand. The RFduino microcontroller that we chose was programmed using the RFduino library version 2.3.1, and the code was written in Arduino development environment version 1.6.1. We designed the firmware to take readings of the 3 sensor parameters once every 15 minutes based on a timing interrupt. Upon taking the sensor readings, the values are then stored to the device's FRAM at the location determined by the FRAM pointer. If the user holds down the interface button at any point while the firmware is running, the RFduino-enabled Bluetooth transmitter is turned on, and the blue LED is also turned on to indicate to the user that the device is attempting to connect. If the device is successfully paired to the mobile device before the pairing timeout, the microcontroller time is synced to the mobile device time. Any data that is stored on the device FRAM is then streamed to the device, and the FRAM pointer is updated. Bluetooth is then turned off, and the device goes into ultra-low power sleep mode. The device will only wake up again when the interrupt occurs, either after 15 minutes or due to a button press. Future iterations of our device, hardware and firmware, will be designed for power optimization and user interfacing. The system could be made more robust by replacing the Arduino with a more powerful microcontroller. We would also like to add displays to the user interface to provide data and information directly to the user without the need for mobile pairing. Additional sensors, such as an accelerometer, could also be integrated to provide additional data correlation. Our mobile application was built for the Android platform, using Android Studio 1.1.0. The application is integrated into our smart device used for detecting drug abuse. The pages have been built and designed using XML sheets, and the application behavior is programmed using the Java language. The design pages are shown on the slides here. The lowest Android API our application can use is 18 Jelly Bean. This application connects to the smartwatch device via Bluetooth Low Energy. It uses the generic attribute profile to maintain the connection and transfer data between the mobile and the application. The device monitors pulse rate, skin conductance, and skin temperature, and wirelessly transmits this to our mobile application. The mobile application behavior can be depicted using a flow diagram. On starting the application, a splash page is displayed, following which the login screen is loaded. If the user is a returning user, login credentials should be entered before proceeding. In the case of a new user, a new account should be created. On login, the user is taken to the dashboard, where the user's real-time data can be seen as long as he or she is connected to the device via Bluetooth. The mobile application, as well as the device, has been enabled to store data. This gives the app the capability to monitor results for a specific time frame. The data streaming in this application is stored in a CSV format, which can be accessed using the Plot Data button, which allows the user to check individual vital signs for any given period of time. The user can click Check button next to the display to list the stored CSV files. A substance detection test is run on the file selected by the user. If data for all 3 physiological parameters exceeds the specified thresholds, an alert pops up signifying a requirement for further medical testing. Our mechanical design was based on a synergy between the PCB and the enclosure. It was designed in SolidWorks and manufactured in two parts, one part being the main frame housing the PCB and the battery pack, the other being a covering. It was 3D printed using ABS Plus thermoplastic in the 3D printer at NCSU's Hunt Library Makerspace. It features a compact design with easy access to the charging port and on-off switches for the device and the Bluetooth. Cavities were provided for the pulse rate and temperature sensors. Each unit weighs about 25 grams and costs as little as $15 to print. This is our low-powered wearable substance monitoring system. It features an enclosure that was 3D printed specifically for our device. It has opening ports for charging. It also features openings for the temperature sensor and the heart rate sensor. And when we look inside, we can see our device under the battery. And now I'm going to talk to you about each of the parts. This part is our microcontroller, an RF Arduino, used as a Bluetooth transceiver. These op-amps are used for our galvanic skin response circuitry. This is our infrared temperature sensor. This is our FRAM memory IC. And this is our heart rate sensor with its corresponding LEDs.
To connect to our device via Bluetooth using the Android app, you first press the push button on the device to activate it. You can then scan for the device from within the Android app and connect to it. Once you do this, data values such as temperature, heart rate, and skin conductance will begin streaming in from the FRAM on the device. Data is saved within CSV files within the app. To check a particular file, we can click on the check button on the home page and see a list of files. When a file is selected, it will be analyzed for a potential substance intake event. A simulated dataset was put into the app for testing. This dataset is being shown to the right side of the screen and should generate an alert page if all three parameters meet a set threshold value.
Please tweet us your questions at hashtag VCACS2015_P03. Thank you. Okay.